Good morning, class. I'm hoping these notes will help you to work with our melting and freezing point graphing activity and analysis questions. So hopefully you are able to follow our scatter plot or line graph guidelines and created the graph for the melting and or heating and cooling of naphthalene. If you have, then you probably moved on to the analysis questions, and you might want or need a little bit of background into matter and its phases. And so I've created this lovely little note set just to help you out and get you a little bit of background information. And you might need to do a little bit more research on your own. So matter and its phases, here we go. We talk a lot about the kinetic molecular model of matter, and that might seem like an awfully lot of words packed into one little piece here. But if we just break down what this is, it looks like this. If we're talking about kinetic, we're talking about an energy, and we're talking about the energy of motion. Molecular refers to be made up of atoms and molecules. A model is simply a representation of something, so it's either too large to do it any justice or too small to study it directly. And matter, of course, is anything that takes up space and has mass. So when we're talking about the kinetic molecular model of matter, we're talking about the different phases of matter, solids, liquids, and gases, and how they are represented in a model form, looking at the motion of their molecules. So there it is, all broken down nicey nice. So if you know that anything that takes up space and has mass is matter, you probably know that there are four phases of matter, or states of matter. So solids, liquids, gases, and plasma. We usually just don't even talk about plasma because it's not anything we can physically study in class, but the rest are. So I'm going to focus on the three big ones here. Solids, we talk about as being definitive in volume. They take up a very specific volume or space, and they have a very definitive shape. It's very rigid, hard to move if it's a solid. Okay, and the molecules in a solid are going to be very tightly packed together with very little movement. I say little movement because the molecules are shimmying and shaking just a little bit. There's absolutely movement even in a solid. Um, the molecules are never stopped. Okay, so there is still a little bit of kinetic energy in the molecules that make up solids. And so here would be a very classic representation of a model of a solid. You have very uniform and tightly packed molecules or atoms together. Liquids, on the other hand, if you're looking at the model, you can see that those same molecules are a little bit more spread out. Now, what this model doesn't show you is that those molecules, those atoms, have a little bit more free movement to move around, and they have more energy, so they'd be moving just a little bit faster. And so because of that, liquids don't have a definite shape. They take the shape of whatever container that you put them in. However, liquids do still have a very definite volume. They still take up a very specific amount of space, but that space they take up can be in whatever shape the liquid is in. So when we add energy into a system, the solid phase can transition into a liquid phase because there's more energy in those molecules, and they start to move around a little bit more, and their structure becomes a little bit more fluid. And then, of course, gases. Gases have the highest amount of kinetic energy in their molecules, between their molecules, and those little lines coming from the molecules represent a lot of motion, very high energy. They're winging around all over the place. They could be bouncing off of each other. There's just a lot of motion in the molecules of a gas, which is why gases can expand up to into great spaces. So there's no definite shape for a gas, and there's no definite volume. gas molecules can be compressed and squished together and expanded up to, fill the room that you're in. Okay, so there's a lot of rapid motion in those gas molecules. Enjoyed that lovely little video. I always wanted to work with glass. Moving on, just a quick recap. Solids have a fixed volume, fixed shape. Liquids have a fixed volume and a free shape, and gases have a free volume and free shape. Now, here's another representation of this kinetic molecular model where the little lines outside the molecules, or the arrows, represent movement or motion. So solids are more compact and very little movement. They're very rigid. Liquids you can see have more free movement and can spread out more. And then gases, again, have a lot of energy. So they're winging all around. They have a lot of motion. Okay, I'm going to go ahead and skip these for you, but they are kind of fun to watch. I should actually make you listen to the Giants for Life, but I won't, for the sake of trying to keep this down a short enough period of time that you all will hopefully make it through. So phase change diagrams are one way to represent what is happening when you take heat energy from the environment and you add it to a substance or a system, and what happens when you release that heat energy or remove the heat and cool a substance or a system. You're probably very familiar with this version of a phase change diagram. Here you have water as ice in its solid form. And as we're adding heat energy to the system here, you can see that it is transitioning from its solid ice version by melting into its liquid version. So melting is a phase change. You have a solid to liquid transition here. And then when you are in your liquid phase, you would have your evaporation or boiling, right? So this was ice, solid to liquid form is melting, and then from liquid form to this vapor or gaseous form, you have evaporation, also boiling. Would work. And that's another transition. You have a liquid to a gaseous transition. So that's when you add heat to a system or a substance. And then the reverse happens when it starts to cool. If you remove the heat from the system or the substance, the gas is going to condense back into its liquid state. And if you continue to allow it to cool, this liquid state will freeze back into its solid state. Okay, and then sublimation, I'm not sure if you know, is the direct transition from a solid to a gas. You've probably seen or heard of dry ice, which is solid carbon dioxide, and when taken out of a supercool freezer, it goes through sublimation. Okay, and the reverse of that we call deposition. So when you remove the heat in a very, very fast manner, you can get this gas to solid transition. So it's a lot of cycling, and it's all dependent upon heat energy. Now there's another way to think of phase change diagrams, and this is through a graph. And so if I were looking at water again, and I was looking at heating and cooling it, right? We have a bunch of data here that is representing this phase change diagram for water. I forgot to take that right-hand arrow out, so just bear with me. We can see that if we throw a bar right down the center here, we have very symmetrical heating and cooling patterns for water. And so on the left half, we would be adding energy into this system, which makes sense because we're starting here in the very low negative something degrees Celsius, and we're ending up here in a very high over 100 degrees Celsius. And so that would be your increase of energy. And on this other side, you could see over time, energy is decreasing. So we're removing heat from the system because it's going from over 100 to back to those super negative temperatures. And of course, this is all very perfectly symmetrical, just to show you the basics here. It might not be this obvious that there is this exact symmetry between heating and then cooling. Okay, but what is really happening here? At negative whatever this is, water is going to be in its solid state. So during this whole period, the solid is simply absorbing energy until we reach this first plateau region. Now at this point right here, that plateau, represents that phase change. So we would be going from solid water to liquid water, and it's going to take this amount of time and happens very specifically at this temperature, that transition. After that transition takes place, then that liquid substance here is just going to keep absorbing the heat energy until we reach another plateau. And at this plateau, we're going to see another phase change. And this is going to be that liquid to gaseous transition. And it happens at a very specific temperature here. So this is going to be that whole transitioning period, and then afterwards it would just be gaseous water or water vapor, and that would just continue to absorb the energy until you remove it. So at this point, let's say somebody was heating water with a Bunsen burner, this might have been the point where they shut the burner off and then they just recorded the temperature as it begins to cool. So in this next transition, the gas is starting to cool down. Molecules are going to move a little more slowly, so releasing and reducing the amount of kinetic energy until you see it reaches the same plateau. So it's a phase change. It is the opposite phase change here of the boiling. So at this point, this would be the condensing. And you can see that both happen at the exact same temperature. They are opposite transitions, but because it's the same type of transition, a liquid to a gas or a gas to a liquid, it's going to happen at that same temperature. And then as it continues to cool, we're going to be all liquid state through here. As the energy reduces and is given off, and then eventually we're going to hit this transition state again, this next plateau, which would be the same transition as this on the left-hand side. So when this was melting, the opposite of melting would be freezing. Freezing is a liquid to a solid transition, and because of that, it should happen at the same temperature as when heating. Both of these are liquid-solid transitions. It just depends on what is happening with the heat, what happens to the state of matter. And then as you continue to remove heat energy and allow it to cool, the substance will, after this solid transition has taken place, will just remain a solid and will remain whatever temperature the environment is. And so, kiddos, I hope that was helpful enough to help you think about how heat, which is a type of kinetic energy, can change a phase of matter from one to the other. On Monday, we will be reviewing the last assignment there, the melting freezing point lab activity. We'll be looking at your actual graphs that you made and assessing those, and we'll also be reviewing and answering these analysis questions that go with the actual melting and freezing point of naphthalene activity. So I hope this was helpful. I hope you have a lovely day, and I will see you Monday. Bye-bye now.